Hey everybody, today we're going to go ahead and look at fission and fusion. This is a nuclear process. This is what happens inside of the nucleus, and it's two of the ways that the nucleus can change. Essentially, there's two different types of nuclear change that we're going to undergo. We're going to undergo what's called fission and fusion, and these two processes are the opposite. Essentially, in fission, what happens is we take one big giant nuclei and we split it into two small nuclei. I guess I should say one nucleus, one big giant nucleus. We split it into two smaller ones. So fission is to split or to rip or to break apart, and fusion is where we're going to take two small nuclei and we combine them together to make bigger nuclei. Okay, so those are the two processes you should be familiar with, fission and fusion. So let's take a look at fission in a little bit more detail. You don't have to write this down. I'm not going to test you on this, but it is kind of interesting history. Lisa Meitner, Otto Hahn, and Fritz Strassmann in the 1930s were the first ones to discover this process of fission. Actually, technically, it was really Lisa Meitner who came up with the idea, who actually realized what was going on. They were doing experiments with uranium-235, and they kept getting barium and krypton, and they couldn't figure out why. It was actually her insight that actually led them to realize that what was happening is that this big nuclei was splitting into two smaller ones. They kept thinking it was contamination, but it was really the brilliance of Lisa Meitner who put this all together. Otto Hahn and Fritz Strassmann, actually being German in the 1930s. Well, actually, Lisa Meitner was too, but she was also Jewish, and she had to run away in the 30s due to the war, and she ended up not getting credit for this originally. But now we give her a lot of credit because she's actually the brains behind the whole operation. Anyway, so that's just a little bit of history there. I'm not going to test you on that, but it is kind of interesting. Anyway, so essentially what happens with uranium-235 is that a neutron collides with this big giant nucleus, and it splits it into pieces. So we take a neutron and split uranium into smaller pieces. Now, not all nuclei are fissionable, meaning that not all nuclei can be split into smaller pieces. U-235, 233, plutonium-239, and thorium-232 are really the only ones. Again, I'm not going to necessarily test you on that one, but just keep in mind that not all nuclei are fissionable. That's really the key role there. All right, let's take a look at what happens with fission. Now, one consequence of nuclear fission is that we can create what is called a chain reaction, where we take one nuclei that's big and we hit it with a neutron, and then that neutron splits into two other nuclei and then releases two neutrons, which then collide with another one, which releases two more, which releases two more, and you get this constant chain reaction. This was theorized by Enrico Fermi, who posited this idea that you could take uranium-235 and get a chain reaction to continue on and get tremendous amounts of energy from this. This was the first controlled nuclear fission reaction. This was done in 1942 on Stagg Field. Now, that is the same Stagg, not our Stagg Field, but that is the same Alonzo Stagg that we talk about, Amos Alonzo Stagg, I should say. But he was a coach at the University of Chicago, and there's a field named after him. Well, underneath that field is where they did this first controlled nuclear fission. Okay, and that would be a controlled chain reaction. Let me show you a little animation of a chain reaction so you can kind of see what's going on. Okay, so what we have going on here is we have a neutron, and the neutron is going to collide with this uranium-235. Now, as it collides with the U-235, what happens is it smashes it, fission takes place, and then we get two nuclei that are now not there. They're smaller than the original one, and it produces more neutrons. And that's the key, is that we've just doubled our number of neutrons. And if we allow this to keep going, what would happen is those neutrons would then collide with another nuclei and continue that process on. So we would actually get that same thing happening where a new neutron would collide with another one, and that same process would occur over and over and over and over again, and you get nuclear fission. Now, the thing about nuclear fission is the fact that with nuclear energy, we get tremendous amounts of energy from this little bit of material that we have. So uranium-235, when it splits, one atom releases 7 million times more energy than one molecule of TNT. So TNT is an explosive, of course, and if we had one molecule that compared to one atom of U-235, 7 million times more energy. And that's significant. That's a huge amount of energy. 1 mole of U-235 releases 26 million times more energy than 1 mole of methane being burned. So we can't ignore nuclear power because there's so much energy that we can get from such a small amount of material, and hence why we have this nuclear explosion that has such tremendous amounts of energy. So let's continue on here. Let's take a look at fusion. Fusion is the other process where we combine the two nuclei together to create more or bigger elements or bigger nuclei. Stars use this energy. This is what our star does, or the sun does, to produce energy. It does fusion of hydrogen into helium, and then helium into hydrogen. It creates lithium. So we can create bigger and bigger elements by going through this process of fusion. Now this is really the birthplace of all of the elements. We start with hydrogen, combine it to helium, combine it to lithium, and that all takes place inside of a star. And when that star explodes, it shoots all of that material through space, and then that material collects together, creates planets, and creates the rest of the universe. So fusion is actually more desirable than fission, okay, for a couple reasons. One, there's smaller nuclei, which we have on Earth. It's hard to find the fissionable materials because there's not much fissionable material. There's only U-235, you have thorium and the plutonium, so there's not much material that we have on the Earth that can be used for fission. But for fusion, we have a lot of hydrogen, and we can get a lot of hydrogen because it's very abundant, and it's small and accessible. So this fusion process would be very, very desirable for that reason, because there's more material, and we get a large amount of energy. So more energy than we can get from fission. Actually, fusion produces more energy. And also another side product is that we don't have any nuclear waste afterwards. There's no nuclear byproduct that we'd have to worry about. So let me show you fusion. Okay, let me show you a little. Okay, so here's two nuclei. This would be tritium, which is a hydrogen isotope. It's an isotope of hydrogen. And what it's going to do is it's going to collide down here with a deuterium, which is another isotope of hydrogen. Now they collide together. These two isotopes of hydrogens collide together, and that's where the fusion takes place. And notice that we get a bigger nuclei. Now what we have left over is helium, because it now has 2 protons. So as I said before, with the process of fusion, we take 2 small nuclei and fuse them together to create a neutron, or I'm sorry, helium, and also a neutron as a byproduct. So for fusion, it's a little bit better because there's no nuclear waste that's left over. The byproducts that are left over in the fission process actually releases radioactive material. Now, why is it so difficult? Well, it's because of the fact that we have 2 nuclei that are protons. The 2 nuclei that are coming together are protons, which are positively charged, and you're trying to push those positive charges close together, and that's really hard to do. It takes a lot of energy. Essentially, in order to get fusion to happen, you need about 40 million degrees Celsius is required. So you have to have a huge temperature, a high temperature for that to happen, a large amount of kinetic energy in your system to smash those 2 nuclei together. And the only way we can ever do this, and we have done this on the Earth, we have been able to do fusion, but the only way we can do fusion is to set off a fission reaction, a fission bomb, which produces enough energy to cause fusion to happen. So you might have heard of an atom bomb. Well, an atom bomb is fission, and what we do is we use that atom bomb to set off a hydrogen bomb, which is fusion, and we fuse hydrogen together, which then releases even more energy. Okay. Anyway, so the last thing I want to talk about is where we use this. And we use this in what are called nuclear reactors. And there's tons of these things that we have in the planet right now because we get a lot of energy from a little bit of material. And there's a lot of pros and cons to nuclear energy, and that's something we can talk about and debate later. But for now, what is happening in the reactor? Essentially what we do is we use fission. This is what we use in our reactors nowadays. We don't use fusion. It's not possible to do fusion on the Earth unless we're setting off other bombs, and that's not too applicable at this point. And we use controlled fission, and we do this to produce electrical energy. So this is fission that's controlled, and they do this by using what are called control rods to slow down the fission process. So you dip control rods. Here's your reactor core right here, and this is where the reaction's happening, where the nuclear process, the fission is occurring. And you dip these control rods in to control and absorb the neutrons to control the rate of fission. So if you can absorb the neutrons, you can stop that fission from happening and therefore slow down the rate and cool it down. Now, what can happen in a nuclear power plant is that these control rods can fail. The most that can happen is that this nuclear core will melt down. This reactor core will not explode. They never have enough mass to create a nuclear explosion on any nuclear power plant. So in all the disasters we've had, especially the Fukushima one that just happened recently, it never had an explosion that was a nuclear explosion. There was a hydrogen explosion, but it wasn't nuclear. It was a chemical reaction, and it spread radioactive waste into the air, but it never exploded in a mushroom cloud, and it never can, because you need to have what's called critical mass. And critical mass is the minimum amount of mass you need to create that uncontrolled chain reaction that we have in nuclear weapons. Okay, so that's not happening here. And essentially, really, all this does is it creates heat. When the fission happens, it creates heat, which then heats up water that creates steam that spins a turbine that creates the electrical energy. And then we cool this down by creating, bringing in cold water from the outside air, from the outside environment, and we use what's called a cooling tower. So what's coming out of the cooling tower is not radioactive, it's just steam. It's all it is. This is not coming anywhere near the reactive core, okay, the reactor core at all. So this is self-contained, and neither one actually, and all we're doing is the same thing we do with a steam engine, same thing we do in coal burning, except we exchange the coal burning with a radioactive core. Okay, and that's it pretty much for fusion and fission. Hopefully that gives you an idea of the difference between the two, and if you have any questions, I'll see you guys in class. Thanks.